Okay. So I was in the process of describing to you various comparisons between different methods for model comparison, so comparison of comparisons. And we were talking about this business of consistency, whether it actually matters or not. In my view, hardly ever. But it does, trying to be consistent has one particular sort of effect that I need to tell you about, versus trying to have good out-of-sample predictions leads you to a different opposite sort of effect. So let me say what I mean by that. Let's agree to call model 1 the simpler model, and model 2 the more complicated model. If you're making a comparison between models of different complexity. And let's call picking model 2, let's call that a positive. Whereas picking model 1 is a negative. Let's just agree to that terminology. Then a false positive is favoring model 2 when you should have favored model 1. And a false negative is the opposite, favoring model 1 when you should have favored model 2. So everybody okay with that? False positive, positive for plus, negative for minus. False positive corresponds to choose M2 when MDG equals M1. False negative, opposite. False negative, choose M1 when MDG equals M2. So you can, with that terminology, you can see where this is headed, probably. If full sample log scores and these other methods over here try to favor good out-of-sample predictions, and that usually means that you want to work with slightly more complicated models to do a better job predicting, then what kind of mistakes will, let's say, full sample log scores, what kind of mistakes will it make more of? False positives or false negatives? False positives. So more false positives, fewer false negatives. Whereas conversely, in order to be consistent, BIC, so this is LSFS, and this is BIC down here, to be consistent, BIC has to choose somewhat smaller models. And so what kind of mistakes is it going to make? More false whats? If it tends to choose smaller models, in this terminology here, then it'll make more false negatives. It'll tend to choose the smaller model when the bigger model was appropriate. So more false negatives, fewer false positives. So these statements are not normative. They don't have contained within them the idea of one of those particular characteristics automatically being better than the other one. Those statements are simply descriptive. If you have a method that makes more false positive mistakes in order to make fewer false negatives, that could be a better method in some situations when false negatives are the thing you need to avoid. Conversely, when you're in a situation where it's false positives that you want to avoid, then a method like BIC that makes fewer of those would be better. And so essentially what I'm trying to say here is that despite what some people have claimed, you have a guy like Berger who says you should always ignore everything on this side of the page and always go with Bayes factors, sometimes going with BIC if you want, but he has made a big career on writing papers of increasing complexity, figuring out Bayes factors in more and more complicated problems. Okay, fine. But to my way of thinking about things, that's not right, because you cannot say that one of these approaches uniformly dominates the other. They just have different false positive and false negative behaviors for any particular sample size. And you need to work out what those false positive and false negative behaviors are and choose between them according to which kind of mistake is worse in your problem. That's my position. And now here are some simulations that show what I'm talking about here. Oops, that's not what I wanted. So at the top of page 59 in section 1 of part 5 of the organized notes, I mention a few of those objections to the ordinary asymptotics. So the ordinary asymptotics are between in the following: choosing between the models in an ensemble of models, script M, that just consists of 2 models, and keeping that ensemble of models fixed as the sample size goes to infinity. I regard that as a flawed asymptotic calculation for at least the following 2 reasons, one of which I've mentioned already and the other which I haven't mentioned before. Number one, I did mention this before, with increasing n, you'll want to make your ensemble of models grow and include models of increasing complexity to satisfy your desire to do a better job of capturing how the real world really is. And the other thing to say, and this applies especially to those of you who work with economic data, for example, or medical data that unfold over time where you have to wait and enroll more patients and more data equals more time. When data accumulate over time, making n much larger means that you are having to wait a much longer time to get the data, and that threatens stationarity. Because the longer you try to monitor a process, the better chance the process has to drift away from whatever it was doing before and not be the same as what you were measuring before. So that's yet another reason why artificially imagining the world as frozen and then letting the sample size go to infinity without any consequences can often also be misleading, because the longer it takes you to get the data, the more chance there is that the process you're monitoring has changed over time and you don't really have the sort of fake asymptotic situation for a different reason. People in economics, this is really nearly a killer in economics, because you're all the time shooting at a moving target. You're trying to model the world on the basis of purely observational data. I think I probably said this before. The data are almost never on the basis of a controlled experiment. So you have observational data. You're trying to understand what's going on causally in the presence of multiple confounding and watching a process unfold that's not stationary, that's changing every day or week or month. Good luck. That's a really, really hard statistical problem. And epidemiologists have the same problem with respect to watching epidemics unfold, for example. You can't do a controlled experiment to try to stop an epidemic. The data are observational, and another situation of the form good luck to you. So bottom of page 59, there are some versions of Bayes factors that do behave sensibly with diffuse priors on the model parameters. A method called intrinsic Bayes factors, invented by Berger and Luis Paricci some years ago, started this stuff off, and there have been a number of more recent cousins, including the paper that I worked on with Fuskakis and his friend Yanis. Anyway, those versions of Bayes factors that behave sensibly tend to have model discrimination performance that's similar to that of BIC in calibration environments where we're doing repeated sampling with a known data generating mechanism. So I'm going to show results for two approaches here, full sample log scores and BIC. And I'm going to do it in the context of 2 settings, both of them relevant to drug trials. So let's consider assessing the performance of a drug for lowering systolic blood pressure, SBP for short, in hypertensive patients in a phase 2 clinical trial. And suppose that possibly after some transformation, a Gaussian sampling distribution for the outcome variable is reasonable. To begin with, it probably isn't, because systolic blood pressure across a whole bunch of people tends to have a long right-hand tail. So the last time you had your blood pressure taken and your doctor talked about what the normal range was, what's a normal systolic in humans? 120 is already regarded as a little high these days by the doctors. They want you to be something like 110/70. That's sort of where they want you to be these days. 120, you can believe that the drug companies want to get your money, so they want to call you pre-hypertensive at 120 and get you start taking those drugs, right? So the definition of what's normal has changed in the direction of trying to get more money from you by the drug companies. Anyway, so 110, 120, and if you're up around 170, 180, 190, that's severely hypertensive, and we need to do something to get your blood pressure down pretty quickly, or what else will be the result if we don't? What's the bad thing about hypertension? You get strokes, you get heart attacks, and it's what people call a silent killer because you don't really feel bad with hypertension. You just are walking around waiting for a stroke to happen and you didn't know it. Okay. Now, two frequent designs in settings of this type have different goals. One of them is quantifying improvement, and the other one is establishing bioequivalence. So let's talk first about quantifying improvement. In this setting, I want to estimate the mean decline in blood pressure under a new drug this new drug I'm developing. And so you might well make a pre-post or repeated measures design in which you measure systolic blood pressure values both before they begin taking the drug and after the same person begins taking the drug, and then you calculate before minus after for that person. And you wait long enough for the drug to have had a decent chance to act. So the data values, y1 through yn, are going to be the observed difference before minus after, and yi will be that difference for patient I as I runs from 1 to n. And then if we think about those same differences in the population of people we're trying to generalize to, let's let theta stand for the mean difference in that population. So we want to learn about theta on the basis of this random sample from that population of size little n. Now, when we're in the world of phase 2 clinical trials, the purpose of such a trial is to decide whether to take the drug forward to phase 3. In other words, the purpose of this experiment is to make a choice, to make a decision. And yet, as I think I've mentioned to you before, the latter half of the 20th century was dominated largely by the frequentist paradigm that did not have much to say about practical day-to-day decision theory. And so as a result, there was a big emphasis on inference in settings where decision was really the appropriate thing to do. And so like it says here at the bottom of this page, at the top of the next one, under the weight of 20th century inertia, in which decision-making was strongly and incorrectly subordinated to inference, your first impulse might be to treat this as an inferential problem about theta, but it's not. It's actually a decision problem that involves theta. And so this brings me to my fourth principle of the four that I think I've shared with you in this section of things. We had the calibration principle, we had the modeling as decision principle, we had the prediction principle, and now we have the decision versus inference principle, which says we should all get out of the habit of using inferential methods to make decisions because their implicit utility structure is often not anywhere near what you ought to be doing. And so the way you play this game now is you notice that people are using things like hypothesis testing to make decisions, and you reverse engineer what they're doing. You work backwards to figure out what utility function implies that particular behavior, and then you look and see if that utility function is sensible, and I'm about to show you that often it's not. So here the action space just has two actions in it. Script A just has A1 and A2 in it. Either don't take the drug forward to phase 3 or do. And so A1 stands for not taking it forward. A2 stands for taking it forward. Now a utility function is going to have to depend both on which action you pick and also what the truth is about theta. And in fact, if you think about it, if I developed a drug that lowered hypertensive people's blood pressure by 20 millimeters of mercury, and I had another drug that lowered it 25 millimeters of mercury, the second drug would be better than the first one for people who were severely hypertensive because it would make it easier for them to get closer to the goal of not being hypertensive anymore. And so actually, up to a certain point, the utility function should be monotone in theta. It should get bigger as theta gets bigger because the bigger the effect, the more useful the drug is at helping really hypertensive people drive their blood pressure down. But that's only up to a point, right? Because if you're sitting at 190, for example, and we manage to drive your blood pressure down by 150 millimeters of mercury, then you've already either fainted or maybe you're near death, okay? And so we can't take that out forever, but for a while, around starting at 0 and going up from there, the utility function should really be monotonic increasing in theta. However, in order to make a comparison between hypothesis tests on the one hand and Bayesian model comparison on the other, which will allow us to compare BIC and log scores, I'm going to compare two models that dichotomize the theta range. And now your first impulse, again, under the inertia of the 20th century, would be to dichotomize them at theta greater than 0 or theta less than or equal to 0, standing for improvement versus no improvement or making things worse. But in fact, 0 is not the right place to dichotomize at, because if I did manage to come up with a drug that was effective, but it only lowered people's blood pressure by 1 millimeter of mercury, then there's no point in taking it forward to phase 3 because it doesn't have a big enough effect. So like it says at the top of page 62, despite a century of textbook claims to the contrary, there's nothing special about theta equals 0 in this setting. And in fact, in most settings that people test the null hypothesis, that theta is exactly 0. And in fact, you know scientifically that theta is not exactly 0 for the reason I mentioned before, because the outcome variable is conceptually continuous. So what matters here is whether theta is greater than a number capital delta, where capital delta is a what I'll call a practical significance improvement threshold, below which the drug is maybe making things better if capital delta is positive, but not enough better to be worth advancing to phase 3. And for instance, any drug that did not lower systolic blood pressure for severely hypertensive patients by at least 15 millimeters of mercury would not be worth going forward on. Theta is the truth in the population if everybody in the population took the drug. So delta is independent of theta. It's a number that we choose based upon our practical significance understanding of the meaning of theta. It does not. This is going to be a benefit-only analysis here, not a cost-benefit analysis. And that's a good point, too. A more thorough analysis would be weighing costs against benefits with a even more complicated utility function than the one I've got here. I'm going to pretend that the standard deviation in these normal distributions is known to make the story even simpler to talk about, but there's little, there's no loss of generality here. It just makes things that are normal turn into t distributions when you have to learn sigma squared. Nothing big about that. So suppose we have little information about theta external to this experimental data set because it's a new drug with a whole new chemical signature that we don't have any information about before. Then what counts in this situation is the comparison of model 1 and model 2 at the bottom of page 62, equation 27 and 28. And model 1 says, both of them say that if you knew what theta was, the yi's would, given theta and the background information, would be IID normal with mean theta and variance sigma squared, and we're going to pretend that sigma is known. But model 1 says that theta, given the background information, is diffuse on the interval from minus infinity to capital delta, and model 2 says, no, it's diffuse on the interval from capital delta to plus infinity. So actually, this is a way to take what Frequentis would call an hypothesis testing problem, where we're testing the null that theta is less than or equal to capital delta against the alternative that it's positive, bigger than capital delta. It's a way to transform an hypothesis testing problem into a model comparison problem, because we can just build the hypothesis constraint into the prior. And then we have exactly the same story that Frequentis would do, except we get to bring in prior information if we have any. Okay. Now, right away, I have 3 different ways I could think of comparing those 2 models in a collaborative fashion, by which, again, I mean creating a whole bunch of data sets where sometimes model 1 is right and sometimes model 2 is right, and looking to see how well each of these methods recover known truth. One is full sample log scores. I'm going to pick model 2 if its log score is bigger than the one for model 1. Another one, look, I could just base things on posterior probability. Let's make a model M star that has the same sampling distribution, but just takes the position that theta is diffuse anywhere on the whole real line. And then we could choose model 2 if the posterior probability that theta was big, namely bigger than or equal to capital delta, under this model star and with the data vector is large. For example, we could say, let's pick model 2 if that posterior probability is bigger than half. And then a third possibility would be BIC. Let's choose model 2 if BIC for model 2 is smaller. You remember how that works. Is it true in this setting here that model 1, or rather model 2, is more complex than model 1, or do they have the same order of complexity? Same order of complexity. So even so, I'm going to call choosing model 2 over model 1, I'm going to call that a positive, because that's going to correspond to deciding to take the drug forward to phase 3. And I'm going to call model 1, choosing model 1, a negative. And that corresponds to the usual terminology about null and alternative hypotheses here also. You set the null up to be the thing, the straw man, right? The thing you don't want to be true. And then you try hard to reject the null and favor the alternative and come up with a positive result that the drug really works. So I'm still going to call choosing M2 as I'm going to call that a positive, and M1 I'm going to call it a negative. And so here I did a bunch of simulations. I set capital delta to be 15. I set sigma to be 10. I let the sample size range from 10 to 100. And I moved the data generating thetas from 11 up to 19 in increments of 1. And I don't know why there's an alpha there. That's a typo. There isn't any alpha happening here. And then I did 1,000 simulation replications for each of those settings. And when I used full sample log score, I made Monte Carlo approximations of those predictive ordinance based on 10,000 posterior draws. And so now I'm going to plot for all these pictures, I'm going to plot for you Monte Carlo estimates of the probability that model 2 is chosen. And so you'll recall that model 2 should be chosen when theta data generating is at least 15. So at 11, 12, 13, and 14, it should the probability that model 2 is chosen should be small, although it would be expected to rise. Right at 15, it should be a half, and then above 15, it should go bigger than that. And so that's exactly what you see. So obviously, if you pick out any particular n, like n equals 10, which is the solid line there, the bigger the data generating theta is, the bigger the chance of picking the model that says the theta is big. No wonder. And in fact, apart from Monte Carlo noise, all 10 of those curves go right through the point 15 comma 1/2, as they should. And the other thing to notice is that as little n increases, does the model discrimination ability of full sample log score get better or worse or stay the same? It gets better because the target behavior, if it were doing perfectly, would be what? It would be completely flat at 0 until you got to 15, and then it would jump all the way up to 1 from that point on. And so slowly, as n runs from 10 to 100, it's slowly trying to move in that direction. All right. The posterior probability picture is identical to the one from full sample log scores. Even though the full sample log score and posterior probability methods are quite different and they're processing the data in what appears to be algebraically quite a different way, their information processing ability in discriminating between the models is identical to within Monte Carlo noise. And that's already pretty interesting because log scores don't measure directly the posterior probability of anything happening, and yet if you use the rule, choose model 2 if the log score for model 2 is bigger than the one for model 1, and you use a different rule that says whenever the posterior probability that theta is greater than delta exceeds a half, those two rules in this problem here are identical in their model discrimination ability. Moreover, BIC, it turns out BIC and the posterior probability approach are algebraically identical here, so all three approaches have exactly the same behavior in this problem. So anybody who says that BIC is always better than log scores hasn't looked at this example where they're identical. Now, what about the other standard, another standard situation in which we'd be wanting to compare one model with another? This corresponds to what people call bioequivalence. Here, there's a previous hypertension drug B, and let's call the new drug A. And now this brings in monetary considerations like Jeffrey was asking about. You're wondering if the mean effects of the two drugs are close enough to regard them as bioequivalent, because then if drug A costs less than drug B and they have the same effect on people, then you'd want to go with drug A. So a good design here would again have a repeated measures character in which each patient's systolic blood pressure is measured 4 times. You'd go before and after taking drug A, and then also before and after taking drug B. It's a kind of crossover design, allowing enough time to elapse between taking the 2 drugs for the effects of the first drug to disappear. So we'd have 4 numbers for each person in this design, and what you'd calculate for each patient is SBP before under A minus SBP after under A. That's how much of an improvement drug A provided, minus the same thing for B. And that will be my Y sub I for patient I, that thing in equation 29 for patient I, and let's let theta stand for the population mean difference having the same character. Again, in this setting, there's nothing special about theta exactly equal to 0. And as before, you know scientifically that theta is not exactly 0. For bioequivalence, as long as the average effect of each drug differs from the average effect of the other one by no more than blah blah, where blah blah is certainly not 0, you would say they're pretty much bioequivalent. And so again, you have to pick a practical significance threshold, but it will probably be a smaller number now. What matters here is whether the absolute value of theta is less than or equal to some number lambda, where lambda, which is a positive number, is another practical significance threshold, this time for bioequivalence rather than for measuring improvement. And you might pick a number like 5. If the 2 drugs differ in their average improvement by no more than 5 millimeters of mercury, then you could call them bioequivalent. Now, assuming as before a Gaussian sampling story with sigma again known and little information about theta external to the experimental data set, now we have a comparison of model 3 and model 4 in which, just as like models 1 and 2, the second line of the model is the same every time. If you knew what theta was, the yi's would be normal theta sigma squared with sigma squared known. And now you build the hypotheses into the priors again. In model 3, theta is diffuse on the region from minus lambda to plus lambda, and in model 4, it's diffuse on the region outside of that, either below minus lambda or above plus lambda. Again, a natural alternative here is based on Pasteur probabilities. Again, we could have that same M star, and we could favor M4 over M3 if the Pasteur probability that theta was big, in other words, either big on the high side, bigger than lambda, or smaller than minus lambda. If that Pasteur probability is greater than 1/2, we'd favor model 4 over model 3. And as was the case before, and I didn't really emphasize it fully, a careful real-world choice between models 3 and model 4 would be based on a utility function that quantified the costs and benefits of the following 4 things. Claiming the 2 drugs were bioequivalent when they were, that's a good thing, and you should get a reward for that. Concluding that they're bioequivalent when they're not, that's a bad thing, and you should get a penalty for that. Deciding that they're not bioequivalent when they are, that's another bad thing, you should get a different penalty for that. And judging that they're not bioequivalent when they're not, and that's another good thing, and you should get a reward for that. So really doing it right, you'd have to build a utility function that had at least those 4 numbers to put in, and then keep score based on those 4 numbers. But here I'm again simply going to compare the calibrative performance of those 3 approaches, just seeing how often they get one model right over the other one. And so I pick lambda equals 5, and I hold sigma still at 10. N runs from 10 to 100 as before. And now the data generating theta DGs run from minus 9 to plus 9 by 2, and also stop right at 0. And again, the alpha is irrelevant. And again, I have 1,000 simulation replications and 10,000 Monte Carlo draws for the full sample log score. Now, I've mentioned this to you already. It has previously been established that when making the often unrealistic sharp null comparison, theta exactly equal to 0 versus non-zero in the context of this model, as n goes to infinity, full sample log score selects the theta not equal to 0 model with probability going to 1, even when theta dg is 0, which is referred to by the consistency people as inconsistency of log scores at the null model. And people like Berger use that as a stick to beat people like me with, or to try to anyway, claiming that means that log scores should be dismissed as a model comparison method. But that's actually, I think, quite wrong. Instead, we should ask for your sample size. For instance, if you have 40 observations, each of those methods is going to make different mistakes with respect to false positive and false negative. And you can ask yourself what those rates are, which sort of mistake is worse in your particular setting, and decide accordingly. So here's a little more complicated picture, but it will show you, if you study it for a while, it does just what it should. I'm going to always plot for you the probability that model 4 is chosen. And so in the region from -10 to -5, we should be choosing model 4. And so everywhere you look, that particular probability is bigger than a half. In the region from -10 to -5. And again, in the region from +5 to +10, it's always bigger than a half. And indeed, the picture is symmetric around 0. Now, in the region from -5 to 5, the right thing to do is to choose model 3, according to whatever the data generating theta is. And you can see that always in that region, the posterior probability of choosing model 4 is less than a half. But in fact, the chance that model 4 is chosen varies with how far theta is from -5, and also how big the sample size is. And does it seem to be here? I seem to have only shown it for 10 up to 50 so that the curves don't write over each other too much. Does it seem to be having the behavior you'd expect as n increases? Is this behaving like it should? Because the asymptotic behavior as n goes to infinity, we should have a +1 out to -infinity all the way up to -5. Then it should drop precipitously down to 0, stay there, and then go back up again to +1 right at 5 and keep going. Can you imagine that in your mind? And these curves are all trying to do that. They're moving more. They're moving toward that goal as n increases. Yes, please. Completely diffuse. It's an improper prior. That's right. Well, that's equivalent to a proper Gaussian prior with an enormous variance. It really doesn't matter. Yeah. For location parameters, you can generally get away with improper priors because they have exactly the same effect as a Gaussian with a huge variance. So, well, okay. How about posterior model probabilities? They behave a little differently. The qualitative behavior is identical. I'm going to flip back and forth between them. So watch it flip. And it's exactly on the same vertical scale and exactly the same horizontal scale. And I think even more or less exactly in the same part of the page. And so this is, whoa. Sorry. This is full sample log score. This is posterior model probabilities. Full sample log score, posterior model probabilities. In fact, if you notice it, posterior model probabilities do a little better than full sample log score did. See how the n equals 10 line is higher in the middle for log scores than it is for posterior model probabilities. So, okay. So the qualitative behavior is identical. There are some numerical differences, and actually posterior model probabilities do a little better. So log scores are not identical to posterior model probabilities here, but they become identical as n goes to infinity. BIC, in the qualifying improvement case, the BIC, the one I showed you before, they were algebraically identical. Here, the BIC and posterior model probability methods nearly coincide. And so BIC is behaving like posterior model probabilities, and log scores are behaving qualitatively the same, but not with quite the same numerical values. So now let's do a comparison between full sample log score and BIC. And this would also apply to full sample log score versus posterior model probabilities. Can you say across the entire range of data generating theta that one of those methods completely dominates the other one? Well, got to think about it. Between -5 and 5, what do you want? Big or small? Small. And so between -5 and 5, BIC does better than full sample log scores. But outside of -5 to 5, you want big. And look, log scores are better. And so actually we have the trade-off I was showing you. You cannot say that one of them is better than the other uniformly. It's just that they have a different behavior with respect to false positives and false negatives. In the way I said before, full sample log score has more false positives. BIC has more false negatives. Now, by the time we get up to 50 observations, there's nothing in it between them. They're virtually identical. And anything beyond that, they're behaving identically. So Now, in the context of the first of those two I showed you, the quantifying improvement example, the real world purpose of the experiment was to decide whether to go forward to phase 3. Suppose you were one of those people in the latter half of the 20th century who didn't know about Bayesian decision theory, and you tried to solve this decision problem with a hypothesis testing inferential tool. So you write down a null that theta is less than or equal to delta against an alternative that is bigger, and you try to do that test at significance level alpha. That's the usual thing where if you pick alpha equals 0.05, to do it Fisher's way, you work out the p-value, and if it's less than 0.05, you reject the null. Now, decision theoretically, this is already wrong, because as I mentioned before, the utility function should actually be continuous in theta, rather than artificially dichotomizing the theta space into those two intervals. But even if you temporarily buy into this incorrect dichotomization, to solve the problem properly, you would have to quantify the real-world consequences of each of the cells in this table here. So the columns represent the truth about theta, and the actions represent, the rows represent the actions. Action 1, you will recall, is stop. Action 2 is go to phase 3. Truth is you should stop in the left-hand column, and you should go forward in the right-hand column. And so even with this artificial dichotomization of the utility function, there's going to be 4 numbers that you have to specify in order to do this right. U11 is your reward for stopping when you should, and that will save the company money. U22 is your reward for going forward when you should, and that will probably make the company money. U12 is stopping when you should not have, and that will cost the company money because you didn't move a promising drug forward. And U21 will be going forward when you should have stopped, and that will be a different cost, namely that you cost the company some money to go ahead and try the drug in phase 3 where it will be shown to fail probably. So all 4 of those numbers are relevant to doing this correctly from a utility point of view. That's true. What you can do with it is you can do sensitivity analysis and see how, over a broad range of values that are plausible, and see what that affects, how that affects your decision. I'm not claiming that this is all automatically easy. I'm claiming that to do it right, you have to think about these 4 numbers. That is what I'm claiming. That's right. And U11 is actually easy also because you know how much it would have cost to go forward in phase 3 and find out that it was bad. You know how much it cost to run a phase 3 trial. So U11, U21, and U22, I agree with you, are kind of easy here, but U12 is harder. That's exactly correct. In fact, in our language of false positives and false negatives, which is the false positive box here? U21 is the false positive box, and U12 is the false negative box. And I utterly agree with what you just said. In this sort of world, people don't pay enough attention to false negatives. Basically, if you fail to take a promising drug forward, you may have left a lot of money on the table in relation to your competitors who are trying the same drug right now in their lab, or might be, and they're going to make the blockbuster drug out of it, and you won't because you decided to stop. That's what bothers me about all these false discovery rate, FDR sort of methods that people are using right now for multiple comparisons. All of these methods are terrified of false positives, and they don't have any built-in penalty for false negatives. And that's completely overbalancing your choice making in the direction of being terrified about the false positives. I'll have more to say about that later this afternoon, I hope. So there's our table. Actually, I said that U11 is the gain from correctly not taking the drug forward to phase 3. I said this is clearly 0, but it's not. It's some number that you could work out. It might cost $10,000 to run the phase 3 trial, or $50K, or whatever it is. And then the other numbers we've already talked about. The optimal Bayesian decision turns out to be the following. You should choose A2, in other words, go forward to phase 3, if the posterior probability that theta is bigger than capital delta is greater than or equal to that particular function of the utility numbers. Let's call that cut point U star. The frequentist hypothesis testing inferential approach is equivalent to this only if alpha equals 1 minus U star. And in fact, if you look at the table in the frequentist world that's analogous to this one here, that Mr. Neyman would have told you should be looking at, I think you'll agree with me that it's not a very good table. And I know I've talked about this before because it's always one of my hobby horses, but here it is again. So, truth, namely theta less than or equal to delta versus theta greater than delta. And this one corresponds to H0 false. No, I'm sorry, H0 true. And this one to H0 false. And these are our actions over here, namely choose H0, which corresponds to action 1, versus choose H1, which corresponds to action 2. H0 false, H1 true. H0 says that theta is less than or equal to delta. H1 says that theta is greater than delta. All right, well, this is the Neyman-Pearson loss function. How much do you lose when you choose H0 and H0 is true, according to Neyman and Pearson? Is that correct or incorrect? H0 is true and you chose it. It's correct, so you lose nothing. Similarly, down here, H0 is false, and you chose H1. You lose nothing. In this box here, the truth is that you should have chosen H1, but actually you stuck with H0. So that's a false negative. And Neyman would give that a probability beta, and he tried to make beta small. This box down here is a false positive, isn't it? Didn't we agree that a minute ago? Here, you picked H1 when it was really actually H0. That's a false positive, and he tries to pick alpha to make that chance small. Compare that with this table here, where you're required on utility grounds to think about 4 numbers and combine them optimally. And Neyman and Pearson say, no, you only have to think about 2 numbers. Moreover, what scale should those U11, U12, U21, U22 numbers come out on? If you're working on behalf of the company? Dollars. And what scale does Neyman and Pearson come out on? Probability. The wrong place. The wrong place. Moreover, they force the diagonal entries to be 0. We can convert Neyman-Pearson into a utility function just by hitting everything with a minus sign, right? And so they force the diagonal entries to be 0, which is silly. And they've got the off-diagonal entries on the wrong scale. They've got them on some artificial probability scale rather than a money scale. Now, the implicit trade-offs between false positives and false negatives in BIC and full sample log scores, and the built-in trade-off in level alpha hypothesis testing for any given alpha, they may be close to optimal or not according to the real-world values of those 3 numbers. So what I'm really saying that you should do, really, is you should think about those 4 numbers, and you should do the right thing based upon maximizing expected utility. Instead, if you just chose between one model or another that corresponded to action 1 or 2 on the basis of full sample log scores, that might turn out to be better than Neyman-Pearson, but it's still not as good as thinking about those 4 numbers and doing it right with utility. Similarly, if you chose to decide between Model 1 and Model 2 or Model 3 and Model 4 and so on with BIC, that might be better than Mr. Neyman hypothesis testing, but it's not as good as thinking about these 4 utilities. So the gold standard for me is actually doing the decision theory correctly. And then the question becomes, how close can we get to the gold standard by using one of these methods that might be inferior to it? In phase 2 clinical trials or microarray experiments, when you're screening many drugs or genes for those that may lead to an effective treatment, and from the drug company's point of view, a false negative error, which stands for failing to move forward with a drug or gene that's actually worth further investigation, can be much more costly than a false positive mistake, because you might only have to spend $50K to run the phase 3 trial to find out the thing doesn't work, and you might have just lost $50 million because you missed a good drug, for example. And so that would correspond to U12 being a lot bigger than U21, and it leads in the hypothesis testing approach in phase 2 trials to doing something that most frequentists would regard as anathema. You have to be willing to use a much larger alpha value than the 0.01 or 0.05 in order to drive your false negative rate down. Because you remember, you can't, for a fixed sample size in the hypothesis testing story, you can't make the alpha and the beta simultaneously as small as you want. And as you try to make the alpha smaller, the beta gets bigger. And so if you want the beta to get smaller, which is the false negative rate, you have to make the alpha bigger. And I've done some consulting work with Roche, the Swiss pharmaceutical company, and they ended up, they stubbornly said they want to stick with the hypothesis testing approach. But after I showed them this stuff here, they started going forward with phase 3 using an alpha on the order of 0.45. And we worked that number out by looking at their utility numbers. And so it is possible to trick the Neyman-Pearson theory into getting the right behavior here, but you have to be prepared to use a much bigger alpha than you ordinarily would. In order to not miss those $50 million drugs, you have to be prepared to spend more $50,000 phase 3s that aren't really worth that much, that turn out to be worthless. And using an alpha like 0.45 is a lot closer to the implicit trade-off that's already built into BIC and full sample log scores. Now, for people who like to test sharp null hypotheses, and I've tried to argue that most of the time, almost all the time, that's a silly thing to do, I do need to show you what happens. And yes, please. Simple as opposed to composite, yes. When I talk about a sharp null, I mean theta exactly equal to some singleton on the real number line. And we might as well use 0 because in the 20th century they used 0 so often. That's a special case of the second approach here, where we let lambda go to 0, right? Because as soon as lambda goes to 0, then we're back in the sharp null or singleton null or simple null hypothesis. So I regard this as unwise. In fact, it's particularly unwise here because we don't care whether theta is 0 or not. What we want to know is how big theta is. Is it big enough to be worth going forward to phase 3, both in practical and statistical terms? That's what we want to know. It is necessary to distinguish between problems in which there is or is not a structural singleton in the continuous set capital theta of possible values of theta. Settings where it's scientifically important to distinguish between theta exactly equal to some number theta 0 on the one hand versus theta not equal to theta 0. There are some settings of that kind. One of them is my T problem from UCLA. And by the way, on the 79th trip to the machine, I got a free cup of tea. So it turned out there was a randomization device in the machine after all. And interestingly, what I found I wrote a paper about this actually, and what I found was that in order to have pretty strong evidence with reasonable priors on a reasonable prior on theta, on the alternative that theta was actually strictly positive, you would have needed in order to have pretty strong evidence from the Bayes factor, because you have to use Bayes factors now. Pretty strong evidence from the Bayes factor would only have arisen if I had gotten something like 450 no free T's in a row instead of 78. So I was actually nowhere near the threshold. I was impatient and nowhere near the threshold of really pretty strong evidence that there is no randomization device. 78 falling short of 450. So an example where theta is singled out for structural singleton is the following. The statement, these two genes are on different chromosomes because the strength theta of their genetic linkage would actually be identically 0 then versus these two genes are on the same chromosome, in which case they have a chance to be linked according to how far they are apart. So there's one, and I'm with Berger that that's an example of one. Maybe the Higgs boson or not was one a while ago, but now we seem to think that they've got it, except for what I said before lunch, that really they seem to have is something that's a Higgs-like particle, which brings us back in the world of continuous uncertainty in the vicinity of the theoretical Higgs. Anyway, it does rule that out, and if they are able to interact with each other, then the theta would no longer be structurally zero. That's right. So I'm not going to push it very much. I can't say that there are no problems in the history of science where a structural singleton is appropriate, but I can say what I've said already, which is that in 35 years of doing this stuff carefully, I've only come across one problem in all of the hundreds of problems I've worked on where it really happened to me. And it was that T problem at UCLA. Now, if you don't have structural singletons, sharp null testing is always unwise because A, you already know from scientific context when the outcome variable is continuous that the null is false. And relatedly, it's also silly from a measurement point of view. If you have a conditionally IID normal sample with mean theta and variance sigma squared, and you have a sample size n, your measuring instrument is y bar. And we already know that it's only accurate to resolution sigma over the square root of n. We know that's its standard error. And so that basically tells you, it's sort of like knowing how close your scale for weighing things gets to the right answer. And the answer in this Gaussian problem, your scale is y bar, and its accuracy, its resolution of accuracy is sigma over the square root of n. Claiming to be able to discriminate between theta equals 0 and theta not equal to 0 with realistic values of n when sigma over the square root of n is quite large still is like someone with a scale that's only accurate to the nearest ounce telling you that your wedding ring has 1 gram less gold in it than the jeweler claims it does. You just can't come up with that level of discrimination. And so if your scale is only accurate to the nearest ounce, then you can't possibly you would need a lot of measurements to be able to, repeated measurements, average, to be able to tell that there's a 1 gram deficit in this particular wedding ring. And when you're way below that 1 gram, or rather way above that 1 gram stage in terms of sigma over the square root of n, it's pretty silly to be asking whether theta is 0 or not because your measuring instrument is incapable of telling you what to do. Now, nevertheless, for people who like to test sharp null hypotheses, here are some results. So here I'm going to compare Model 5 and Model 6. Model 5 says that in fact, I'm going to use sigma squared unknown here because I made the calculations. And so Model 5 says, if you knew what sigma squared was, the yi's would be ID normal 0 sigma squared, and then I put a diffuse prior on sigma squared. And Model 6 says something similar, except I don't know what theta is either, and I'm going to make that prior diffuse as well. So now Model 5 corresponds to the singleton that theta is exactly equal to 0, and Model 6 says no, it's anywhere it wants to be on the whole number line. So now a Bayesian competitor to BIC and full sample log scores would be to construct the central 101 minus alpha % posterior interval for theta under Model 6, and then pick Model 6 if this interval does not contain 0. That would be a pretty standard thing that people do all the time in deciding whether hypotheses are right or not. Construct your posterior distribution, build your 95%, let's say, posterior interval for theta, and look and see if 0 is in the interval or not. And if it's not, then you go with Model 6. Otherwise, you go with Model 5. All right, so here's my simulation experiment details. I stick with sigma dg equals 10. I again run n from 10 to 100. And the data generating thetas now go from 0 to 5 by units of 1. I have 1,000 replications. I have 100,000 Monte Carlo draws for the full sample log score. And all the figures below give Monte Carlo estimates of the probability that M6 is chosen. Now, as before, let's call choosing M6. Now we are in a situation where there's a difference in dimensionality. M6 is the more complicated model now because it has 2 parameters and Model 5 only has 1. So let's call choosing M6 when it's not true a false positive and choosing M5 when it's not true a false negative. So here's the behavior of full sample log scores. This is the thing that illustrates the lack of consistency. When theta is 0, full sample log scores don't actually come up with probabilities that are consistent for that. They try to move toward the ideal of a line that is at 1.0 all the way across. In other words, full sample log scores doubt the existence of singletons. But now if we talk about that from the point of view of false negatives and false positives, we can simply say in the limit as lambda goes to 0 in that earlier bioequivalence setup, the full sample log score approach makes hardly any false negative errors, but it makes quite a lot of false positive mistakes. And so instead of talking about it as being out of order because it's inconsistent, let's just talk about it for your sample size 10, for example. You can see it makes hardly any false negative errors because that probability is always at least 0.8, whatever theta might be. But it makes quite a lot of false positive mistakes because it has an 80% chance of saying that theta is not 0 when it actually is. All right. The posterior interval thing has a completely different behavior because its curves are all constrained to go through the point 0, 0.05. They want, basically, they've got an error rate of 5% built into them because it's an interval. And so the behavior of these, this posterior interval approach is quite different. It makes many false negative errors because its rate of false positive mistakes is fixed at 0.05. And so if you're in a world where false positives really matter to you, then log scores in a singleton null situation are probably not a very good choice for you. But if you're in a world where false negatives matter, and I'll show you a singleton hypothesis test later on where they do matter more than false positives, then log scores might be fine. Again, this picture doesn't prove that full sample log scores are bad. It just says they have a lot of false positives and thereby hardly any false negatives. That's just a statement about how they behave. Now, interestingly, when the interval method is modified so that the alpha matches the full sample log score behavior at 0, in other words, if I allow alpha to vary with n, which is a sensible thing to do when you take the idea of sigma over the square root of n being the accuracy of your measuring instrument y bar, when I adjust for that, the two approaches have identical model discrimination ability. In other words, they are processing the data in the same way. They're just taking two different perspectives on how you should trade off false positives and false negatives. And when I modify the interval method to have its alpha match the full sample log score behavior right at 0, and I have to let alpha vary with n, which is something that frequentists typically don't do. But if I do that, I discover that both of them are processing the data, extracting signal from the data in an identical manner. So again, what's built into this picture versus this one is not how much you're learning from the data, but what stand you take about false positives and false negatives. Identical information content, completely different position, implicit position about false positives and false negatives. So we're ready for our next break. Let's stop now and come back at 2:45. PC Ops, I'm turning off now, and I'll come back on at 2:45. Thanks. So let's finish off this stuff. There isn't that much more in here. And then I want to spend much of what time remains showing you a large data example. And then after that, I want to leave at least a half an hour at the end to talk with you about pointers toward future topics, give you some arrows into the literature on things I didn't have time to talk about, and then throw the floor open to everybody to have a general discussion if you'd like to do so. So here we are with these pictures. We saw that one already. We saw that one already. We saw that one already. The behavior of BIC is quite interesting. It has to try hard to be consistent. And so as n increases, it has to try to move even farther down than the 101 minus alpha percent method does. The 101 minus alpha percent method is always going to be stuck in the middle right there at the point 0, 0.05 if you use alpha 0.05. But what BIC is going to try to do is it's going to try to make that point at 0 go all the way down to 0. It's actually going to try hard to make that happen. And so to do that, its behavior is quite different from that of full sample log scores with point null hypotheses and fixed alpha posterior intervals. Its false positive rate does decrease as little n grows, but it suffers a high false negative rate to achieve this goal. So once again, you can't say one method is better than another uniformly. You have to think about the trade-off between false positives and false negatives. And interestingly, when I modify the posterior interval approach to the BIC behavior with respect to letting alpha vary with n, I get the same result again, that the two approaches are processing the information in identical ways. They just have different implicit structures built in about trade-offs between false positives and false negatives. Also, I did a little comparison between geometric and Poisson. Suppose model 7 was that you have count data now, integer valued, non-negative integer valued data, and this is an artificial example because I've never seen a real world case where I would legitimately be comparing a geometric model for count data with a Poisson model, but just to see what happens, I was interested. So you can work out full sample log scores and BIC. They both turn out to have closed form expressions here. I'll put conjugate priors, by the way, on each of the parameters in those models. I created a simulation world where n varied from 10 to 20 to 40 to 80. I set diffuse priors in all cases, and I made 1,000 simulation replications. It turns out that with theta 1, the geometric equal to 1/2, and theta 2 equal 1.0, both data generating distributions are monotonically decreasing, and they're not easy to tell apart by eye. So that would be a situation where both methods would have trouble discriminating between the two because they look the same on the data. So let's call choosing M8 the Poisson when the truth is the geometric a false Poisson error, and choosing M7 the geometric when the truth is Poisson a false geometric mistake. And here's a little table that shows how things go. These are the Monte Carlo probabilities that the Poisson model was chosen. And what you discover is that both methods make more false Poisson errors than false geometric mistakes. I don't know why. And once again, we have a different sort of trade-off. Neither BIC nor full sample log scores uniformly dominates. Each has a different pattern of false mistakes. LS full sample log scores correctly identifies the Poisson more often than BIC does, but as a result, BIC gets the geometric right more often than full sample log scores. So the conclusion here is that I'm going to skip some of that stuff and leave you with some takeaway messages on page 91. In the bioequivalence example, even when you unwisely let that lambda go to 0 and test a sharp null hypothesis, in my view, the asymptotic behavior of any of these methods, and particularly log scores, is irrelevant. What counts is the behavior of log scores and base factors with your sample size and the models being compared. And for any given n, it's not possible to say that the false positive, false negative trade-off built into base factors is universally better for all applied problems than the false positive, false negative trade-off built into log scores. Or vice versa. The answer is you have to think it through in each problem. And here are some examples where the tendency of log scores to choose the bigger model in a nested model comparison is exactly the right thing to do, exactly the right qualitative behavior where you would want to go with log scores rather than BIC. So we were just talking about this at the break. Imagine you're trying to do variable selection and searching through many compounds or genes to find successful treatments. Here, a false positive mistake, taking an ineffective compound or gene forward to the next level of investigation, costs the drug company C dollars, but a false negative error, failing to move forward with a successful treatment in a highly competitive market, costs K times C, where K might be on the order of 10 to 100. So that would be a situation where you'd be more worried about false negatives than false positives, and you'd be willing to absorb a fair number of failed phase 3 trials in order to find that big blockbuster drug. Also, in a 2-arm clinical trial setting, look at that random effects Poisson regression model we were looking at before. The YIs, again, are counts of relatively rare events, and the XIs, the indicator variable 1 for the treatment, 0 for control. Now, you would consider fitting this model instead of its fixed effects counterpart, which is obtained by setting the error variance, the random effect error variance to 0, and you would fit this model to describe unexplainable heterogeneity. That's this Poisson over dispersion problem. And now in this problem, base factors will make the mistake of telling you that sigma squared E is 0 when it's not, more often than log scores. In other words, it will make a lot more false negative mistakes in order to have a false positive mistakes, that's right. And log scores will make the other error, telling you that sigma squared is positive when it's actually 0 more often than Bayes factors. So each of them makes a different pattern of mistakes. But actually the mistake that Bayes factors makes is much worse than the other mistake, because if you go around thinking that sigma squared E is 0 when it's not, you'll end up underpropagating how much uncertainty you have about the thing that you care about. And so all throughout this investigation, beta 1 is the thing we care about, and the width of the uncertainty band for beta 1 depends a lot on what sigma squared E is. And if you go around pretending that sigma squared E is 0 when it's not, you're going to get an interval for beta 1 that's too narrow. And so you're going to miss the boat on the thing that you care about the most. All throughout this discussion, it's vital to keep in mind the following point, that the gold standard for false positive, false negative behavior is provided neither by Bayes factors nor by log scores, but instead by Bayesian decision theory in your problem. You have to think things through if you're going to try to do it carefully. And I think I'll just skip over the rest. I've shown you already this stuff about how to recalibrate the posterior predictive p-values. And then there's a summary here, pages 97 through 104 that you could read through again to remind yourself of what we did. But I will come to the last page, 104. Decision theory works well, Bayesian decision theory works well when there's only a single agent making the choice. That could be a single person, or it could be some sort of organization or collection of people who figure out some way to be content with the idea of acting in unison. However, now there's a new question. How can good decisions be arrived at when the you in you should maximize your expected utility, when the you is a collective of individuals, all with their own utility functions that imply partial cooperation on the one hand and partial competition on the other? An example is any problem involving allocation of finite resources by two or more people who have agreed to band together in some sense. And that's essentially the definition of politics, is the allocation of scarce resources. That's my definition of politics, anyway. At the level, it could be at the level of family, for example, because the people in the family have different ideas about how the money should be spent. Your teenage daughter wants you to spend $25,000 on a car, and maybe you and your wife don't want to spend that money that way, and so on. So allocation of finite resources by two or more people who have agreed to band together but who have different utility functions. That's a classic example here. Or also politics at the level of a nation, or you can just go on. The one that I work with all the time in my work with Kaiser is one that I've mentioned before out loud, I think. Defining and funding good quality of health care. The actors in the drama are at many levels: patient, doctor, hospital, state regulatory body, local regulatory body, federal regulatory body. And all of these people are in partial agreement and partial disagreement on how and how many resources should be allocated to the problem of addressing this particular patient's immediate health needs. And so Bayesian decision theory is puzzled by problems like this. There are no optimal solutions anymore. And so is any other kind of decision theory anybody has invented so far. This is an important, hard, unsolved problem that needs more thought than it has received so far. I told you about Arrow's theorem that says basically it's impossible to keep everybody happy when there's two or more people and they don't agree on their utility functions. And Kadane's theorem that goes a little farther and says it's impossible to guarantee that two Bayesians will agree on what to do unless they're two or more, unless their utility functions are identical or their posterior probabilities are identical. So those sound like impossibility results that make it useless to study this problem, because it just looks like if there's one of you, then there's a good way to behave, and if there's more than one of you and you're in competition, then there's no good way to behave. But that's an unsatisfactory state of events. I think that all of us could, with profit, spend more time thinking about this problem and trying to come up with ways that, if not allowing everybody to get what they want optimally, at least trying to find some point that in some collective sense comes as close as possible to everybody getting most of what they want. That's the kind of thing that you'd want to do. And people have not developed theories based upon that sort of trade-off yet that I've seen. Maybe it's just a question of of my not knowing that literature that well. Another example that I want to show you briefly of the kind of thing we were doing with the calibrating posterior predicted p-values. I asked the students, as I told you, to in my class at Santa Cruz this quarter to do simulations in which they compared the actual variance to mean ratios in the treatment and control groups of the in-home geriatric assessment example with what you'd get if you were to simulate from actual Poissons with VTMRs in 1. And there's what you get when you do it. The control VTMR, if nothing was going on, distribution, of course, is centered at 1.0 and goes down to about 0.8 and up to 1.2 with the sample size that we have. And the observed VTMR is out there about 1.65. And so we don't even have to compute a tail area. Everybody can see that that's so far away from what you'd expect that the Poisson model is drastically called into question. And the same thing is true in the treatment group, although not quite so strongly. So it's the same kind of thing. When comparing a point with a density, the most natural thing to do, according to Fisher, is to work out a tail area. But actually, interestingly, when comparing a point with a density, that's the same problem we faced with log scores, right? Because we wanted to know whether a particular point was consistent with the predictive density for it. Okay, I would like to spend much of the rest of the time showing you an example involving a large data set, and I put that on the course webpage. I seem to have forgotten. Interesting. I have forgotten to post the data for you. I have the data myself, and I forgot to post the data. So I'm going to show you what happens here, and then when I get, I think on Sunday, I'll try to fix the web page. So to run this R code, you're going to need to change directory to where several files are. This is data from a randomized controlled trial in which the subjects were randomized either into the treatment or the control group. And it turned out that there were about 24.5 million people available to be randomized, giving rise to treatment and control groups of about 12.2 million observations in each of them. So we'd all agree, I think, that that's big data. So now I want to get into R and change directory to where that stuff is. So let's do that. These data have been altered from their actual behavior in real life to preserve confidentiality. So I'm going to go to that place called large data example, and I'll remember now, in fact, I'll write myself a note right now to do it, to put the data on the web page, sanitized data on the web page. So here are my files. I have the control data, the treatment data. I'm going to show you in a little while the treatment data with some spikes removed, and I think that fourth one is not relevant. So let's run my code. I'm supposed to unbuffer the output. Did I remember to do that yet? No. So randomized 24 million subjects into two groups. The outcome variable y turns out to have lots of zeros. And in this version of the data, the non-zero values have all been scaled to live between 0 and 1 for confidentiality reasons. They lived in a different range before, but I've rescaled them. What you need to know about this outcome variable is that big is better than small, and that the thing that people care about as a population quantity of interest is the treatment population mean minus the control population mean relative to, in other words, divided by the control population mean. So this is we're looking for a relative change, a relative improvement in the treatment story over the control story relative to the control story. So that's our population parameter we're trying to learn in the data. Most of the data is zeros, so we have about 90% zeros and 10% non-zeros, but that still gives about 1.1 million non-zero observations in each group. So I go ahead and assign some values, some variables called things like number of treatment zeros, number of treatment non-zeros, and I work out make sure that I have a total, and I look to see what proportion of the treatment numbers are zero, and it's about 90.7%, and I bring the data in, and so let's do some of that stuff right away. And so we have about 1.1 million non-zero values. And I'll do the same thing with the control. 90.73% zeros in the treatment group, 90.72% zeros in the control group. That's a very small relative difference. The control group has a tiny edge, only about 0.02% in generating fewer zeros. In this sanitized data set, that's going to be overwhelmed by the difference in the means in the non-zero part. Let me go ahead and bring this stuff in now. Okay, now, if you wanted to do a simple two independent samples analysis based upon the central limit theorem, you could just pretend that the story in each group looked a lot like draws from a normal curve, and you've got the normal curve for the treatment group with a mean and a variance, and the normal curve for the control group with the mean and the variance, and you could go ahead and do the two independent samples thing. Now, of course, that's a silly model for this data because 90% of the numbers are zero. And I'll show you in a minute of the other numbers, they all have an enormously long right-hand tail. But on the other hand, there's another way. Yes, please. All the numbers are non-negative. 90% of them are zero. And of the ones that are non-zero, all of them live strictly between 0 and 1 inclusive. So they reach the value 1, but they go down close to 0, but not at 0. So that's a sort of silly way to justify making an analysis based upon the means in each group. But there's another way to justify such an analysis that does not involve the normality assumption at all, namely the central limit theorem, which says that as long as the variance in the population you're sampling from is finite, the distribution of the sample mean will get closer and closer to the Gaussian the more and more numbers go into that mean. That is actually a non-parametric approach to doing inference. Because if what you care about is the population mean, the central limit theorem says it doesn't matter what the population distribution looks like. If you have enough data, the sampling distribution of y bar is going to look a lot like a normal curve. And so there are two ways to motivate the usual large sample Gaussian story, or the usual Gaussian story. One is to pretend that each group comes from Gaussian distributions. The other one is to hope that the little n's are big enough that you can use the non-parametric result that arises from the central limit theorem. Well, the first way to justify the comparison of the means is, of course, silly here because we have violently non-normal data. But 1.1 million numbers in the non-zero group might well be enough data that we would have a pretty nice normal curve if we looked at the repeated sampling distribution of y bar, even when we mixed in all those 11 million zeros. And actually, that's an empirical question because, as you know, the central limit theorem says you will eventually get a normal curve as n grows, but it doesn't say when. Little n is big enough. And I could, if you forced me to, I could create a density for which the repeated sampling distribution of y bar is not yet normal with n equals 50 million. I could do that if you made me. The central limit theorem may be very long in arriving as a useful result for us. And in particular, in a problem like this, we can wonder if it's going to work well because, yes, we have 12 million observations in each group, but the distribution, as you're about to see as we go along here, is violently, violently non-normal. So those two things tug against each other. Who will win in the tension that leads to the resolution of the central limit theorem? Well, I'm going to go ahead and show you the analysis based on the sample mean and the sample variance anyway. And then we can compare it with parametric analyses. And then also I'm going to compare it with the bootstrap analysis. Yep. Yep. The way I would do it is I would generate distributions that come increasingly close to having infinite variance. Because if you allow the variance to be infinite, then you lose the center limit effect altogether. For example, the Cauchy distribution has no center limit effect at all. So I would start building sampling distributions for you that are closer and closer to Cauchy. In fact, we could do it by creating a mixture that is blah blah percent of the time Cauchy and 1 minus blah blah percent of the time something else that does have finite variance. And I can just let the proportion of Cauchy go to 1 fast enough that whatever n you tell me, I can give you something that doesn't behave right. So that's how you would do it. I mean, it's pathology, you understand. But the fact remains that nothing in the central limit theorem by itself says how big the n needs to be to get a good normal curve for the repeated sampling distribution of the y bar.
So that explains why I can't ask you to do the step. And then in the limit, say, well, look, I can get you as close to affinity as you want, and you tell me you're not normal.
No, actually, I'll just get as close to the Cauchy as I want. I'll put the weight on the Cauchy. I'll make the weight on the Cauchy approach 1, but not ever quite get there. And I can always stay one step ahead of you. If we play the game where you tell me the n and I have to find something that exceeds it, then I'm always going to be able to beat you. So yeah. All right. So how far did we get? We read in the treatment data. We read in the control data. So now I'm going to show you the Gaussian analysis, or at least the large sample analysis. So here's the y bar for treatment. It comes out about 10 times 10 to the minus fifth, and there's its standard deviation, which you will note is an enormously bigger number than the mean is. So I'm going to go ahead and print both those things for us. Yes, I'm about to. Let's just work out the coefficient of variation for this data set, which is the ratio of the standard deviation divided by the mean. So the noise to signal ratio on this data set is about 14. That's fairly noisy. The standard error of the treatment mean is, of course, the usual s over the square root of n, and that comes out on the order of something times 10 to the minus seventh. Then I can do the same thing for the control numbers. They're actually quite a bit smaller than the treatment numbers are, and I can work out the control standard deviation and the standard error, and then work out the standard error for the difference of the means if I were interested in differences. So let's go ahead and do all that stuff. Oops. Did I forget to read in something? Oh, full control sample. I never read it in. That's interesting. Ah, okay. Didn't I? Tell you what. I've been talking too much. Let me kill this off and start again. Lose track of where I am. What's that? Oh, good. Thank you. I'm going to unbuffer also. Everything go according to plan. It's pretty good so far. I'm down to relative difference in zero abundance. Okay. All right, so let's look at what happens. The standard error for the difference in means is really tiny. Y-bar treatment minus Y-bar control over Y-bar control is a whopping 75%. And so in this particular data set, the treatment was better than the control by 75% in relative terms. Obviously, that's going to turn out to be not only large in practical terms, but also in statistical terms, because the standard error is going to be much smaller than that. And the signal-to-noise ratio we get in our inferential question will be enormous. So the conclusion is that the overall treatment mean, zeros included, is about 75% bigger than the overall, and that should ascend than the overall control mean. Now you can do a Delta method calculation in which you, this is based on a Taylor series expansion to linearize the particular function we're interested in, because the function we want is of Y-bar treatment minus Y-bar control over Y-bar control, and that's a function of two random variables, so you have to do a little Delta method calculation to work out what its standard error is. And if you don't remember how to do that and you want to know, you can email me and I'll tell you. And so the standard error calculation comes out only about 1 percentage point, whereas the estimated effect is 75 percentage points. So we have a pretty strong signal-to-noise ratio in the data. The z-score on the percentage or relative comparison scale, the signal is about 70 times bigger than the noise. So obviously that's enormously statistically significant. And if we wanted to finish it off by going ahead and building a 95% interval, we just go 1.96 standard errors either way. And this is an approximate Bayesian analysis with diffuse priors. The posterior distribution has 95% of its central mass between about 73% improvement and 77% improvement on this, with a difference this big and with a sample size this big. All right, so this is a non-parametric analysis. No assumptions have been made about the underlying control or treatment CDFs. We've just been hoping that the CLT operates on a distribution with a sample size this big, with 90% zeros, and as we'll see in a moment, an extremely skewed histogram for the non-zero values. So that sets up a tension between a little pro-con argument. The pro for the central limit theorem, very big sample sizes, and the con against is violently non-normal. So let's take a little while to look in a detailed manner at the non-zero treatment values. So I do a quantile on them to see, and they run from about 1 times 10 to the minus 7th all the way up to 1.0. And I'll go ahead and make a histogram of them. And you see that they have an extraordinarily long right-hand tail, which cries out for a log transform, right? So let's go ahead and log them and make a histogram of the log. And something else cool comes right out. Now we get something that's starting to look sort of Gaussian on the log scale, but it also seems to be a mixture of a discrete distribution with a continuous distribution, because there's a lot of spikes in the data that are much higher than the normal curve, let's say even a mixture of normals would have expected here. So if I were building a parametric model for this data set, the first component, I'd be building a mixture model, and the first component would be a point mass at 0 of unknown height, and I try to learn that height from the data, and I would be able to learn it very well indeed with 12 million observations, 11 million of which are zeros. I think I know that relative frequency pretty well, right? The second component would involve some sort of model for this stuff, and what occurs most naturally to me is to see if the values that those spikes take on have any direct meaning to the people with whom I'm consulting. And if they do, we can treat them multinomially, because the values they take on would be known to us, and the only thing that would be unknown is the population frequencies with which those values occur. And so that suggests to me trying to build a 3-part model. First of all, a big old spike at 0. Secondly, it's going to turn out that what I want to do is to locate the 500 tallest of those spikes and subtract them out as a second component in the mixture model. And I'm going to treat that component multinomially. with known locations along the log non-zero treatment scale and unknown heights, and then learn those multinomially. And then what's left, I'm hoping is going to be relatively smooth, and then I can look at it and see if it looks Gaussian or perhaps maybe a mixture of Gaussians, for example. So let's have a go. Let's take a closer look, for example, between minus 12 and minus 11. I picked that out because the biggest spike of all seems to be between, well, here, no, not the biggest one, but this interesting one here seems to be between about minus 12 and minus 11. So let's go ahead and make a little table of all those values between minus 12 and minus 11. And you see that the data actually end up having a discrete character, even though the values are immensely, I mean, how many significant figures is that? 2, 4, 6, 8, 10, 12, 14, 16, 17 significant figures. So we now learn that R is definitely working to what used to be called double precision standards in the old Fortran days. But notice that some of these spikes occur with much greater frequency. The one right here has 1,125 people located at that point, and there are others that have hundreds. Here's one with 412 and so on. So this suggests to me, let me remove the spikes and treat them multinomially, as if their locations were known and all that's unknown are the relative frequencies. So the code to do that takes quite a while to run. And so in the interest of time here in the course, I went ahead and deleted the 500, the spikes with the 500 highest frequencies. I deleted them from the data set, and I'm going to be modeling them multinomially in parallel to what's left. So I'm going to go ahead and read those guys in. And that turns out to have 611,000 roughly values still left of the roughly 1.1 million non-zero values that we started with. So we're looking at the treatment data here. We had about 1.1 million, and a bit over half of those values are left in the part that's left over after I pull out the spikes. Pardon? Yeah, so let's plot. So now I'm going to plot a picture in which I show you both with the spikes and without. Oh, I forgot to take the log. So those are the non-zero treatment values. Let me go ahead and take the log and then make the histogram. So the picture with all of them in there is the bottom picture, and the picture with the spikes removed is the top picture, and you can see that having taken out the 500 most frequent spikes, what's left does look pretty close to continuous. It's just sort of mumbling, a little bit of mumbling up and down around some sort of continuous trace. I actually took them out of the data set. I found all the points of highest, the data points of highest frequency, 500 highest frequencies, and simply removed them from the data set. And the resulting smaller data set is histogrammed up here on the top. That's correct. I made a picture with 1,000 histogram bars for about 611,000 observations, and so it looks conceptually continuous, even though it itself is actually a series of little discrete guys as well. What is that Charlie Chaplin said? Comedy is tragedy at a distance. That was one of his maxims. If I could attempt to stretch quite a distance here, everything that's discrete looks continuous if you stand far enough away from it, right? Which is basically what we're doing here. Okay, so the distribution of the log treatment values, there they are again. That sort of reminds me of either a normal curve or maybe a mixture of a relatively small number of normal curves. So let's try that. So like it says here, the distribution of the log treatment values with the spikes removed suggests fitting either a single normal distribution or a mixture of, let's call it capital G, greater than or equal to 2 normal distributions. The models for this can be set up readily in WinBugs or RJAGs, but with 611,655 observations to do the mixture modeling for the mixture of normals the calculations would need to be done by parallel processing to result in realistic clock times, and even then it would take a long time. So the Bayesian calculation here does not scale well in sample size. So I'm going to illustrate a maximum likelihood approximation to it using a function in R that does mixture modeling called mclust. So here, if you're going to do this yourself, you have to install the mclust package and then you have to load it. I've already installed it, so I'm just going to go ahead and load it with the library command as usual. And the people who wrote this code at the University of Washington get in our face about this. By using this invoked on its own or through another license package, you accept the license agreement in the license file, whatever that might be. I suppose what it says is, since you, something like what the Winbugs people say, since you paid $0 for this, that should be the value of the answer that you get out of it, and don't sue us if anything goes wrong. That's probably what it says in the license file, because that is definitely what it says in the Winbugs file. Okay, now I can run this command. It estimates the mixture model with capital G equals 2. So you just say, call the function capital M lowercase clust, and you name the data set comma G equals 2, and then you put the model names in. There'll be various things called $V something or other. So, okay, so let's run it, and then I'll see what it says the answers are. This will take a minute or two, I think, on a big data set like this. The method that maximum likelihood is using is something called the EM algorithm, which is a way to guarantee that you are always climbing up the log likelihood hill. That every time you move, it's always it only can do the two things. It either can stay at the same height on the hill or it can go up. And it will definitely arrive at a local mode of the log likelihood function, but it will not guarantee convergence to the global mode. It has it built inside itself its own idea for starting values. It didn't even ask me for starting values, you'll notice. So it generated its own starting values, and actually in a relatively small amount of time it produced the following results. Given that I told it there were two mixture components, it says, okay, they have about 50-50 probability. About 47.5% on component 1 and about 52.5% on component 2. The means are actually not that far apart, and the variances are what you see right down here. All right, so that was pretty good. Now I want to see if that fits the data any decently. So, because it's the first thing bigger than 1. If you want to, you could. Well, it's hard to fit 1.1 normal curves together, right? Now, if you allowed this technology to decide what it thinks is the optimal G, what do you think it's going to say with 611,000 observations? Is it going to mention a big G or a small G or in between? It's going to mention a really big G. And in other words, it's going to end up probably overfitting the little local bumps in the actual density function. And so I think the right way to do this when you have an enormous amount of data is to start small and go bigger, and only go bigger than a particular point if you need to. So I could have drawn a picture for in which I would show you what the result is by fitting one Gaussian to the data, and you discover it doesn't fit that well visually. And now let's see what the mixture of two Gaussians. Let's see what that looks like. So I wrote a little function. First, let's go ahead and get the data again. But this time on a little bit of a blown up version. So these are the log treatment values with the spikes removed, and now I ask it to make a histogram with only 100 histogram bars in it. So I wrote a little function that plots the density of a mixture of Gaussians. You have to tell it the points at which you want to evaluate the density, and the vector of probabilities that represent weights across the different components, and the vector of the means and the vector of the standard deviations. And it will work out what the G is from how long the P vector is, and go ahead and do just what you see right there. Basically, it's just adding in, starts with 0, and it adds in 0, the previous value plus p times the normal curve with those means. So it's not very hard to write that function. And I assign to p the answers I got from the m-clust function, and the same for mu, and the same for sigma. And then I go ahead and fit the story and see what happens. And look at that. The mixture of two normals fits the data almost perfectly. And so I would conclude that a good parametric model for this data set is as follows. A spike at 0. It's a mixture model with three components, one of which is itself a mixture. A spike at 0, a bunch of spikes that are treated multinomially with known locations and unknown heights, and I learned the heights from the data. And what's left when I subtract those spikes out, a mixture of two normals, where I learned the mean and variance and the weights for those two normals. Now, it's possible to program all that stuff into RJAGs, for example, and let it fly on the whole data set. That would be unwise, because you would then have 12 million observations being read into RJAGs, and 90% of them are zeros. And since that whole thing is going to be treated binomially for whether it's a zero or non-zero, you ought to treat that part separately. But now let's talk about the other parts. Well, okay, I could fit the multinomial part separately, and that wouldn't be very hard also in RJAGs, but there would be about 500,000 observations in there for it to fit the multinomial to, with known locations and unknown weights, unknown heights, and that would take quite a while. And then the Bayesian approach to the mixture of two normals would take a very long time, because the way that the MCMC goes for mixture models is you have to create a latent variable that equals 1 if that particular observation belongs in mixture component 1 and otherwise equals 2. And you have to update those latent variables in each row of the MCMC data set. So think about how big the MCMC data set is here. It has a column for the first component of P and a column for the second component of P. It has 2 mu's and 2 sigmas, so we're up to 6 parameters so far. And then it has 611,000 columns, each of which is an indicator for whether that observation belongs in mixture component 1 or 2. And as you look down the column for each observation, it'll flick from 1 to 2. Some of them are always going to be in 1. For example, where my mouse arrow is right now, it's always going to be in mixture component 1. And these ones over here are always going to be in mixture component 2 for all the rows in the MCMC data set. But the ones in the middle, around -7 or so, so they're going to flip back and forth. Some of them are going to be 1 sometimes and 2 other times, and the other way, vice versa, and so on. So you have to carry around inside your code an MCMC data set with about 611,000 columns and as many rows as you feel like getting monitoring iterations on after an appropriate burn-in. That is going to take a while. Even if you break it up and Hadoop it across many processors, it's still going to take a while. So we have now reached the point in the class where we need some sort of approximate Bayesian calculation, because the exact calculation is probably going to take too long, even parallelized on a lot of processors. So what to do instead? So I conclude that a good parametric model for the treatment values in this experiment is what I just said, a mixture model with 3 components, a large spike at 0, and I learned that probability, it's around 90.7%, 500 smaller spikes at known locations with unknown probabilities, and I learned them multinomially, and a mixture of 2 normal distributions for the data with the spikes removed. And a similar parallel analysis on the control group data yields the same basic parametric model over there. So what I would need to do is run a big model on the treatment stuff, run a big parallel model on the control stuff, get posterior distributions for everything that matter. In particular, I need to monitor the mean on the actual data scale as a function of all the stuff in that 3-part model I said to you, in order to be able to have a column of those means coming out of the MCMC work for the treatment group and another column from the control group, and then I can start pasting them together to get mean of treatment minus mean of control over mean of control. So there's quite a bit of work to do, and all the different steps involved in that would take an enormously long period of time if I tried to do them in a full Bayesian fashion. But there is another non-parametric alternative, namely the bootstrap. And I want to talk about the bootstrap a little bit before I run the code. So I have some pages over here that talk about the bootstrap. I have increasingly, as part of this work, come around to the view that the bootstrap is a valuable approximation method for Bayesian non-parametric calculations when the sample size is large. And the idea is as follows. Let's consider the treatment group in this large data example I just showed you. Before any of the data values y sub I arrive, your model that is based only on the science of the problem would be, I'm going to see a vector of n numbers, where n is large, all of them are real numbers, and my uncertainty about them is exchangeable. That would be the stuff that comes directly from the science of the problem, and only the stuff that comes from the science of the problem. Collect all that stuff together into the place called script B, the background information. Now, De Finetti showed that this is equivalent to a model where you think of the data, you start thinking about the cumulative distribution function in the population you're trying to generalize to, and call that capital F. If you knew what an F was, the yi's would be ID from F, and F has to have a prior distribution. So that would lead directly, if we tried to make that operational by putting a prior on the first row there, that would lead directly to Polya trees, Dirichlet process priors, the things I showed you 2 weeks ago and last week. Now, suppose that F has finite mean mu and finite variance sigma squared, and these are innocuous supposes. I should probably have put them into the background information, because you will never in your life ever see real data that has an infinite variance, except for the data set, nearly so the data set I have to create to try to beat him. Okay, the optimal model specification goal, and you remember I defined that some lectures ago, it's the answer you would get from not assuming anything that wasn't given to you by the context of the problem. In other words, I don't want to go around and say, what's the posterior from you given the data and the background information and the spurious assumption that the data come from the following parametric family. I don't want that because I don't know if that's right or not. I'd like to condition only on the stuff that I know that came directly from the science of the problem. Bayesian nonparametrics may provide this, but in fact the way you have to make this operational has a lot of bells and whistles and grunting steam engines as part of it. I think I showed you some of that the other day. It's actually not that easy to do, and even when you do it, the computational time will be prohibitive with large N, even with parallel processing. Now, it can be shown, and I recently proved a theorem that shows this in a special case, and the theorem works in broader generality as well when I finish the details, that the following thing is true, that particular posterior that I want is approximately given by, and it's a good approximation. In fact, it's a very good approximation with 1.2 million non-zero values and 12 million overall values. Namely, it's very well approximated by the bootstrap distribution of the sample mean with many bootstrap replications. Now, the thing that's different from how you may have run bootstraps before is that capital M, the number of bootstrap replications going into the bootstrap data set that this picture is based on, may need to be really large to overcome how non-normal things are to really get an idea what's going on, to really flesh out the right tail of this non-parametric density here. I'm accustomed, when you read Efren and Tibshirani's book, they talk about capital M equals, in the early days, Efren ran the bootstrap with 500. And even then, people complained because that took the desktop computers they had too long back in the late 70s when he first started doing this. Then he and Tibshirani were suggesting numbers like 1,000 to 5,000. For this problem, I suggest to you on a data set as non-normal as the one we have here, you want to be thinking more like capital M equals 100,000 to 1,000,000, a really big number of bootstrap replicates. The good news is that the bootstrap is absolutely the most ridiculously easy parallelizable algorithm that anybody could offer you. How do you parallelize the bootstrap? You do the same thing in parallel on all of your processors, right? So if you've got K processors, you just give capital M over K replicates to each of them and then pull the results at the end. I mean, that wasn't hard, was it? So this is extraordinarily easy to parallelize. My machine has 8 CPUs, so a million isn't going to take that long. With 1.1 million observations in the non-zero part and 1 million bootstrap replicates, it took about 8 hours at 2.8 gigahertz on a single node in this machine here. So I can get that down to about 1 hour by parallelizing across all 8 CPUs in this machine. Now, what's cool about this approximation is that this latter bootstrap distribution is much faster to compute, even with large values of capital M. It could, even with a lot of cluster components, a lot more than 8, for instance, it could take days to get the Bayesian nonparametric answer, maybe even several weeks to get a good version of the Bayesian nonparametric answer. Because I've been finding that to get good Monte Carlo accuracy out of Bayesian nonparametric methods, the number of rows in the MCMC dataset also has to be in the millions. And each row in the MCMC dataset takes a lot longer to create than each bootstrap replicate. A lot longer. Might be a factor of 100. So what we're doing here is we're using a technique that was invented by a frequentist, Brad Efron, to approximate an answer from a Bayesian point of view. And one of the reasons that that's a reasonable thing to do is that when you, I think I may have mentioned this to you before, when I talked about the bootstrap earlier this term, when Efron first wrote about why his bootstrap confidence intervals work, his proof of why they work was Bayesian. His proof said basically, actually, the bootstrap distribution should be close to the right Bayesian posterior distribution with a flat prior, and so that's why this works, because we know that Bayesian posterior distributions give good interval estimates. That was essentially his proof. Now, if I wanted to do this and finish solving the problem, I can now bootstrap both the treatment group and control group separately to get the Bayesian nonparametric posterior approximation for the mu in the treatment group and the mu in the control group. And then when I'm done with that, I build a little Monte Carlo data set because these particular columns are all IID. So I have a column from UT. Here are all the bootstrap samples. Here I have a column from UC. Here are all the bootstrap samples. And so in each row, I can just go that mu T minus this mu C over that mu C. That becomes the theta star estimate in that row. I could call this thing here theta 1 star equals that down to theta capital M star. And now this is my bootstrap approximation to the Bayesian posterior distribution on the thing I care about. So these things can then be combined to create IID draws from this guy here. So let's do that just on the treatment data. And see what sort of numbers we get. So I wrote some code to do that. There are bootstrap functions in the R world, but it's easy to write your own function. All you just do is run the sample command with replace equals true, and you get bootstrap sample, so that wasn't very hard. So now I'm going to run this code right here, and it's going to take a while to run, which is why I want to make sure I've got the buffered output on. Okay, so let's run it, and you can see that it's already 3:41. I don't think we're going to get our results until about 4:15 on this, so we're going to talk about some other stuff in the meantime. That's taking quite a long time to get each one, and I asked for 1,000 of them, so yeah, this is going to take a while. I did it this morning or in the middle of the night, and it took about half an hour, so I think we're okay. All right, good. So let's talk about some other stuff while we're waiting for this code to run. Something we've been doing to try to borrow strength appropriately is described here on this page. You have run an experiment now that had a randomized controlled character where those 24.5 million people were randomized into two groups of 12.5 million. The Bayesian impulse, if it's available, is to try to bring in information external to those treatment and control groups to strengthen your estimation of the thing you care about. And the standard way to do that from a Bayesian point of view would be to use exchangeability arguments to find either control groups or treatment groups external to this one experiment that you judge to be similar enough to what you got from this experiment that you can combine information across them in a Bayesian hierarchical way like we did with the aspirin meta-analysis. Remember, we built that hierarchical model which had the property that it pooled information in a non-naive fashion. It asked the question, how heterogeneous are these things? If they look like they're completely homogeneous, then I'm just going to throw them all into one data set and pool them completely. But if they look like they're somewhat heterogeneous, then I'm going to do partial pooling based upon how different they are. So we already know how to do that from the earlier part of the class on random effects models and hierarchical mixture models in meta-analysis. So suppose additional control data sets that you judge to be exchangeable with the one you got in this particular trial are available. And that's going to be slippery because you're going to have to think about how you can find control groups that weren't part of the control group in this particular experiment that are similar to what you have here. And you may not have such a thing available to you in your world, but you may if you think about it. Then a hierarchical random effects model like the aspirin meta-analysis I showed you before can be used to synthesize all these data sets. So suppose we have a total of k control groups, of which the first one is the one that actually came from this experiment. So this experiment, EXPT, gives you the treatment group and the first control group. And suppose you have k-1 other ones that you find possible to do a partial combining on exchangeability grounds. You can then get each of these posterior distributions with the bootstrap, and you can combine them, if you do it right, to get an overall analysis that borrows strength across the data sets. So what you'll get when you're done is a posterior for theta that conditions not only on the treatment group, that's not mu, that's wrong. This is supposed to have been YT, blah, 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 blah. YT, YC1, down to YCK. So what we want when we're done is a posterior distribution that has compiled all this data together, but not in an obvious naive pooling fashion. We didn't just throw all the control groups together into one enormous vector and go from there. We do a kind of partial pooling based on the random effects models that will provide sharper inferences than those that are available from the posterior just based upon YT and YC1. And I don't think I have time to show you how to do that today, given that we want to try to do a full wrap-up. But I can show you that another time, or you could write to me. Write to me, and I'll write back to you about how to do it. Okay. Let me see what else I have here. I began to write out a series of pointers to other topics. A number of you raised other issues that you wanted to ask about in the course of this course, and so I have a few things to say. One of them is the topic of missing data, and I have two books to recommend to you on this subject. The first one is by a guy called Mike Daniels and another guy called somebody Hogan. I don't know Hogan, but I know Mike Daniels. And it's a few years old now, but it's still the definitive book on this. Their book is called Missing Data in Longitudinal Studies, Strategies for Bayesian Modeling and Sensitivity Analysis. And I happen to know this book is really good because I was on the committee of the International Society for Bayesian Analysis that was charged with sifting through about 15 or 20 books to decide which of them was the best Bayesian book published within a particular year. I think it was around the year 2010, for example. And I read all 20 of the books, actually, which was time-consuming but fun, in order to really wrap my mind around what's going on in the Bayesian story lately. And this is one of the books that was nominated, and it didn't end up winning, but it almost ended up winning. It came very close to the top, and so I can recommend it to you highly. Even if you don't have longitudinal studies, you're going to learn a lot by reading this book because you watch how they deal with missing data in longitudinal studies, and that'll show you how to do missing data analysis with non-longitudinal studies. So Good book. That's a full Bayes book. An approximate Bayes book is written by Rod Little and Don Rubin. The second edition came out in 2002. It's called Statistical Analysis with Missing Data in the Wiley series. And Rubin has been a fan for decades now of a technique that he calls multiple imputation as an approximation to a full Bayes analysis. I'm not sure with MCMC. He first started talking about multiple imputation way before MCMC came along. And I'm not sure in a world that has MCMC and MCMC that runs quickly with parallel processing and fast MCMC algorithms, whether we really need to do multiple imputation, but there's software out there for doing it. Rubin is a guy who likes to make a nickel off what he does, and so I don't think he has ever made his multiple imputation software available as freeware through R. I don't think that's true. I think you have to pay him, his company, which is based in Ireland, to minimize the taxes. You have to pay his company to get a copy of the software to do the multiple imputation thing. So here we are. What I wanted to show you was the basic idea can be sketched. We're up to 550 iterations, so it's churning along pretty nicely. Suppose we have data with a regression structure. So this is the variable y, the outcome variable, quantitative, and we have x1 through xk as our predictor variables. And there's holes in the data. So everywhere there's a missing observation, I'm going to draw a hole like that, a circle like that. And there may even be holes in y. Well, as I think we've spoken about at least briefly earlier, one simple thing to do would be to toss out all the rows in the data set that had at least one hole in them and go from there. What assumption would you have to make in order that that approach does not introduce any bias? That's right, that there's no information in the fact that something was missing. And people call that missing completely at random. That's the name that Rubin invented. So if the data are MCAR, so if the data are missing completely at random, then it's okay to toss out all the rows that have at least one hole in them. But it's not very efficient, is it? Because you might have started with a data set with 1,000 rows and end up with a data set that only has 110 rows in it because there's enough missingness there. So that's not very good. So what should we do instead? Well, suppose we could treat y and x1 through xk as a multivariate distribution of dimension k plus 1. And for instance, the simplest distribution, if it worked, would be to treat it as a multivariate normal with dimension k plus 1. Then you have two tasks here. You have to learn the parameters of that multivariate normal distribution. And you remember how that works. Each row here, I'm going to call it y together with x sub I in this data set, would be modeled as IID draws from a k plus 1 dimensional multivariate normal with mean vector mu and covariance matrix sigma. And mu is a k plus 1 by 1 vector, and capital sigma is a k plus 1 by k plus 1 matrix. So that thing there, given both mu and the covariance matrix, would be like that as I runs from 1 to n, where n is the number of draws here. So look, you have two things to learn. You have the parameters, the mu and the sigmas, and the capital sigma to learn, and you have all those holes to learn, because you'd really like to know what the data set would have looked like if there hadn't been any holes there. So suppose the data really are missing completely at random. Then why not think of building a Gibbs sampler that has two steps? Step one, given our current estimates of mu star and sigma star, fill in the holes predictively. And then step two, given no holes in the data set, estimate mu and capital sigma. And now go around and around. That's a little daisy chain. In fact, it's one of those ham and eggs things that my old high school geometry teacher talked about. You pretend you have the ham and learn about the eggs. You pretend you have the eggs and learn about the ham, and you just go around and around. That's essentially what the algorithms in the book by Daniels and Hogan tell you how to do. And that's something like what Grubin does with his multiple imputation story. What he really does is he creates a data set in which all of the holes have been filled once by making draws from those predictive distributions. Then he creates a second data set in which all of those holes have been filled again. And then he does that over and over again a whole bunch of times. And he invites you to do whatever analyses you would have done on a complete data set on each of those complete replicates. So for example, if all the holes were filled, you might run a regression model where y was predicted from the x's. Run that code over and over again on all those multiple imputation data sets, he calls them. And then he has a little bit of technology that tells you how to combine the information both within each of those analyses and between them using analysis of variance style ideas to get a final inference about how the x's help to predict the y's in a way that has properly accounted for the uncertainty in the holes. And that turns out to be an approximation to this Gibbs sampler Bayes analysis over here. So missing data, when things are missing completely at random, missing data holds no terrors for us. It might take a fair amount of computing to do it right. What if the data are not missing at random? Then you have to have a model that explains why things are missing as a function of the other stuff you know. And that modifies this step here. Given the current estimates of mu and sigma and the other things that you know that you think are predictive of why something is missing, then fill in the holes. And then now that there's no holes, go back and estimate these things. And that's harder because there has to be a model both for how y and x1 through xk relate to each other and a second model for why things are missing as a function of the y and the x1 through xk values. And so you can read about that in that book as well. Well, we're coming into the home stretch on this calculation, so I will return here. That's funny. Looks like I didn't catch all the code down here. All right, and so I'm going to build the theta stars, and I'm going to make the histogram of the bootstrap data set, and I'm going to go ahead and work out the bootstrap interval. So these are the bootstrap values, and theory based upon the multinomial distribution, which defines how the bootstrap works, allows us to prove that that is a good approximation to the non-parametric Bayesian posterior distribution for that theta thing that we're interested in. And in particular, if you want to know where theta is likely to be in a 95% likely sense, you can go in 2.5% to the left tail of this distribution and 2.5% into the right tail. That's what Efren calls the percentile method. And there are refinements to it, but the refinements don't change the answer here. And now I'll just remind you what the previous central limit theorem result was. So now we're getting from the bootstrap 0.732 up to 0.773, and the original central limit theorem result was 0.732 to 0.774. And so we have now answered the question, even with a data set with violently non-normal behavior, 12 million observations going into each bootstrap replicate, and 12 million observations going into each Y bar that you would have used in a repeated sampling way as a frequentist, the result is that that asymptopia has been achieved. We are at n equals infinity as far as the central limit theorem goes. And the earlier calculation we made that didn't involve anything fancy at all from the point of view of any Markov chain Monte Carlo, any fancy calculations that pretended things weren't Gaussian in the limit and blah, blah. Those earlier non-parametric calculations based on the central limit theorem, they turned out to hold up quite nicely against the bootstrap. But the only way you know that is to have done the bootstrap analysis also. So these days, I'm actually quite a big fan of using the bootstrap as an approximation to the Bayesian non-parametric calculation I would like to make, but I'm unable to make in a time limit that's finite enough to actually be useful to me. So this is a paradigm that I suggest to you. Consider bootstrapping the things you care about as a way of approximating your large sample Bayesian posterior distributions that have a fully non-parametric character where you haven't assumed any particular parametric model at all. And then once you've got those posteriors from the bootstrap, you can begin combining them in Bayesian ways, for example, with random effects models to borrow information across different control groups, different treatment groups, and so on. So if you had a series of control groups, each of which had 12 million observations in them, let's say you had 10 control groups you thought were exchangeable with the one you have, then that's a total of 12 groups, 11 groups, control groups, and 1 treatment group, each of which has 12 million observations in it. And so we have 144 million observations. A full Bayes analysis would take so long, even with 8,000 cores in your Hadoop cluster, would take so long that you can't even do it. And yet you could subject that to a careful bootstrap analysis with 1 million bootstrap replicates in each one, with probably a handful of cores, and get the answer overnight. And it'll be a legitimate approximation to what the full Bayesian non-parametric answer would have been if you'd waited for a month instead. So here we go. Well, the main limitations of the bootstrap are that it's based solely on the empirical cumulative distribution function in the sample. And in particular, when you're working with long right-hand tailed data, and you're working with a small sample of long right-hand tailed data, the bootstrap will not necessarily work very well because it has not yet seen all of the tail. So suppose the actual true underlying density was this density here, very long right-hand tail, and suppose you have a sample of values, and then after this we'll take our oh, I just talked right through our final break. Great. Suppose you had a data set and it looked like that, for example. A relatively small sample from a very long right-hand tail data set. Then the bootstrap knows nothing about the right tail beyond the largest value. And so the bootstrap by itself cannot give you a very good answer about any summary of this distribution that depends heavily on the behavior of the right tail. That's where Bayesian non-parametrics comes in. We teach through either parametric or non-parametric modeling. We teach the data process about the portion of the tail it hasn't seen yet through parametric or Bayesian non-parametric assumptions, and then we go from there. So that would be an example where the bootstrap doesn't work very well. No such examples will exist in experiments with large enough data sets to make us want to use the bootstrap as an approximate Bayesian calculation. So I really don't see any downsides to the bootstrap story. It certainly works in all these simple one-sample problems that we've been talking about. Shall we break for 10 minutes anyway, and then come back and have a wrap-up? So let's start again at 4:10.